So welcome back, everybody. Glad to have you here. If I could ask a few more of you to turn your webcams on, that would be terrific. Um, and let's get started. Okay. So welcome to the last lecture of service security. It won't be the last class. We have class next week in which we will do our final presentations. And I'll talk a little bit more about that. Oh, Oh, there we go. My mic was off. All right, welcome back. This is the last lecture of service security, and but it won't be the last class because next week we have uh, the final presentations. Okay, and I'll talk a little bit more about that before today's session is over. So today we're going to do the last module. So we're no longer going to talk about authorization. We've done a few weeks of that. I wish there was more time to do more of that. But we'll talk about client-side security, which is really about browser-side security, but also about any other clients to your API as well. So I want to talk a little bit more what I would call more front-end and web app side security issues. Okay, um, so let me get started. So a little rejoinder to last week's discussion where we talked about single sign-on, and I'll try to share with you today and also next week before or after our final presentations, some recent and interesting developments in security over the past just a few years, maybe just 2 years or so. One has been the addition by Apple of their own sign-in feature, which on one level is not so different from any other company that says, hey, use our single sign-on feature. So Apple offers one as well. What's really interesting about their feature, though, is that it has some extra features. Their single sign-on has some extra features, one of which is that when you sign in with Apple, it allows you to actually use a fake email address. So Apple's single sign-on feature has the ability. I think you have to choose to do it, where instead of providing your actual email address to people, to other companies who are using Apple single sign-on, Apple can provide them a fake address of some kind at apple.com or something like this. And for every website, it can use a different address for you. So this is an interesting innovation from my point of view to single sign-on, where the single sign-on provider, in this case Apple, is actually faking your identity to the other company so that your email address stays more private to you. All right. So this is a kind of interesting thing that's going on with Apple. Apple's also got a couple of other innovations in the past couple of years, and again this year related to privacy. And I'll talk more about those maybe next week. But for today, I just like to kind of mention that I think that the single sign-on feature itself is going to kind of change in the coming years, perhaps with more companies offering this kind of feature, privacy-preserving feature, where even though you're signed in with Apple or Google or whoever, I hope in future more companies will follow this in trying to keep more of your identity secret from companies that are using single sign-on. All right. Okay, so I just want to mention that about single sign-on and what's kind of going on with that right now. Okay, so let me move on. So today we want to talk about what I'm calling client-side security threats. And I want to be clear what I mean by client-side. I mean everybody except the web API, okay? Except for the web API, I want to kind of talk about two things. One is the web application. So we have a web application that's talking to our web API, but right now anybody could talk to our web API. Our web API does not prevent any kind of application or request coming to it. And I'll mention in a moment that that can be really risky. There could be certain routes on the web API that are extremely sensitive, and we want to protect it from just anybody accessing, all right? And I'll talk about why that is. So one aspect of client-side security will actually be about the web applications, communication with the web API. In fact, I'll probably take a third or a half of the time today just to talk about that. The other aspect of client-side security is actually the browser. The browser itself is a trusted agent by two people. First of all, the web application usually trusts the browser to do what the browser does, right? The browser does its own job. And the user also trusts the browser to be a competent agent. However, we'll see today that the browser can get hijacked in many, many simple ways. And simply trusting the browser is not enough. So we'll talk today about how we can prevent injection attacks and forgery attacks coming from the user's browser as well. Because once again, the browser is trusted by a web application and by a user, so we better kind of secure the browser. And we'll see that there are some really interesting tools with which you can tell the browser to beef up its own security. All right. And then the last thing we'll talk about, I think, will be about the content that we are getting from our content distribution networks, which is like our Bootstrap or whatever framework you're using, your style sheets, fonts, JavaScript that you're getting from a content distribution network. How do we know they're giving you the right scripts? How do we know they're giving you the right style sheets? How do we know those haven't been hijacked and changed in some way before they got to your computer? So we also have to make sure that the assets we're getting from third-party sources are valid assets and that those have not been hijacked in some particular way. Okay, so feel free to raise your hand if you have any questions, or else you can just tap them into the chat window. And otherwise, I'll get started. And I'll be covering these in the order in which they are numbered. I'll start with the web application versus web API, then about the browser, and then about the CDN. All right, great. So let's start with this communication between our web application and our web API. Thus far, we have trusted all the requests coming in from our web application. When our web application makes a request to the web API, the API trusts it. Why does the API trust it? So far, the major excuse I've given why we should just trust whatever the web application tells us to do, we should just do it, is because many of the routes of our system, for example, a route to get account information, the route to get project information, the route to get project details or document details, to get the list of projects, etc. All these routes require an auth token, okay? And the web API trusts the application when it makes these requests because the application has to present an auth token. And the application could not have gotten the auth token from any other place other than our API. Our API is the one who generates those auth tokens, and we used authenticated encryption, so it's a kind of signed encryption, if you will, to make sure that nobody can forge this auth token. So this token was a symbol of our trust. So whenever a client comes to us and says, "Here's the token," we trust it because that's the agreement we have. We saw a couple of weeks ago that we can go a step further than that, or maybe last week we saw, we can even generate auth tokens which can be given to other clients. So for example, last week we saw that when you go into your account information, we can provide you a token that you can give to another application. You, the user, can give to another application. We use that extra token which had limited privileges. The scope was much smaller on that token to make some requests from our terminal, some curl requests or something like that, right? So the point is we are using auth tokens so far to trust the client who is asking the API for things. And if you have that token, we trust you unconditionally. We say that you must, first of all, know the user because the user credentials were used to get the token. And second of all, the web API must have trusted this client application sometime in the past or trusted somebody who trusts this application because you have an auth token. So if you have that token, you're gold, okay? Now, unfortunately, that simple rule cannot apply to all our routes. There are some routes for which the client cannot have an auth token. For example, if somebody is coming in and trying to register an account for the first time, well, we don't know who they are. we could not have provided an auth token for them before, right? So they're coming in, they're not logged in, they're just saying, I want to make an account. And the browser is telling the web application, and the web application is asking the API, could I please make an account? Well, what's the harm? Let them make an account. Why do we need to trust this request? Well, for several reasons. One is, if your service is providing some kind of computational or other kind of features, it's possible, or perhaps your service allows people to store some data. It's possible that somebody out there is going to misuse your service by using your computational or storage capacity in some other way. For example, I am allowing people to store documents. Well, maybe somebody's going to get the bright idea that, hey, look, this Credence application allows us to store documents. Why am I paying Dropbox? I can just make, let's say, 100 accounts on Credence, and I can store all my files on Credence. I don't need to use Dropbox. These fools have given me a free storage service, okay? Alternatively, maybe your service is doing some kind of computation, and you don't want just anybody to be able to come in and create some kind of fake accounts, all right? There was an interesting attack on GitHub a few months ago, weeks ago, months ago, where for those of you who are familiar with GitHub Actions, it allows you to do continuous integration. It allows you to run your tests on GitHub. And of course, some people got the bright idea that, hey, we're allowed to run our tests. GitHub doesn't know what a test looks like. We can run basically any code through GitHub Actions. So what they did is they used they created some repos which basically do Bitcoin mining, and they ran that as their tests. And then and they set that as a GitHub action, and they used, like, they asked GitHub to scale that up, and they created like hundreds or thousands of accounts, and GitHub servers are then like mining Bitcoins for them. Okay, that was obviously not the intended purpose of GitHub Actions, to mine Bitcoins. So these are examples of where somebody else can use your service to do something you don't want them to do. So you want to be able to control who's creating an account. You don't want somebody to come in as a bot and create 100 accounts. And remember, a bot can also have, create hundreds of fake emails separately, so they can verify all those emails as well. So we have to control this, but whoever's coming in to register and make a new account cannot possibly have an auth token for themselves yet, right? Similarly, so this is another route also. So this is the route to start registration. This is the route to actually create an account. These are both post requests. And in both cases, you don't have an auth token. The web application could not have an auth token for that user because that user hasn't been created yet. Similarly, for authenticate, the request to say, hey, here's my username, here's my password, can you authenticate me? We want to control who can make this request to authenticate a username and password. Again, why? Because otherwise, somebody's going to create a bot that just tries millions of usernames and passwords to see which one they can get in with, right? And we want to be able to control and say, no, you can't make so many requests. But we can't limit somebody if we don't know who they are, right? So we can't limit a client if we don't know who they are. So this is another route that is for which we cannot provide an auth token because they're not logged in yet, but it could be abused. And similarly with the SSO route as well. So all these routes, who can register, create, authenticate, authorize. In your application, there may be other routes as well, which don't require an auth token. I'll let you figure that out for yourself. But if we cannot require an auth token, how can we validate that this is a genuine request? Okay. So for these routes, I think the thing that we have to do is that we have to make sure for these routes in red that not anybody can make these requests. We have to make sure that only our authorized web application is making this request. Okay. All right. Hold on, folks. Give me a little second here. Okay. All right. So, any questions about this so far? Why these routes are sensitive? why we cannot just trust any application. Any thoughts about this? You can raise your hand, you can type a question. All right. So what should we do? Any ideas? Unless you've seen my slides already. Oh, let me see what's coming in. Retire. Okay, yeah, we can just give up and say, fine, that's all. We can't do anything about it. We're screwed. But no, I don't get paid if I just tell you that. Okay, so we got to do something else. Well, I'll tell you what I do when I have a problem like this. I ask, what do other people do? Right? So what do other companies do with these kind of sensitive requests? So let's take a look. Here's Google Maps, and when you register as a developer for Google Maps to get an API key, they ask you to do something really interesting. They say that you need to they will generate for you what's called a signing secret. Okay. They will create a digital signature for you, excuse me. They will create a digital signature for you that you have to use for certain requests. Meaning, for certain requests, you cannot just make the request and provide your API key. You have to digitally sign it. All right, I'll talk about digital signing again. Try to recall what that means again. You have to digitally sign your requests so they know it's actually you who's making the request. All right. This is another application, TinEye, probably not so popular anymore. It was, well, maybe it's still popular. TinEye is basically a reverse image lookup. You provided an image, it will tell you which websites use this or a similar image. I think Google Images may have a similar feature, but TinEye came up with it first. All right. And they also require a similar thing. When you make a developer account with them, they not only provide you an API key, which we talked about last week, and our application made an API key, an auth token basically, last week, but they also ask you for something else. They give you a, so they give you a private key, okay? And you are required to sign your requests with your private key. So that's interesting. They're asking you to digitally sign your requests to the API. Maybe not all the requests, but certain requests. All right. Twitter, they're doing the same thing. When you create a developer account, they're asking you, if I can zoom in on this, all right. Um, they're giving you another secret with which you will need to sign in and to digitally sign your requests. All right. So it appears that a lot of companies out there, what they're doing is they're saying when you're making certain requests, maybe all requests, but definitely certain requests, you must digitally sign that request using a private key. Okay, so let me just kind of talk about digital signing again, because it might have been a while since we have talked about digital signing in this class. Okay, so digital signing was this. The idea of digital signing was that if Alice wants to talk to Bob, right, Alice can, of course, encrypt her message to Bob, but here's the idea: is if let's say the message is not secret, but Alice wants to prove to Bob that it's Alice who's making this request. Then what she can do is she can encrypt one version of the plain text using her private key. Okay? And remember that anybody who has her public key, which could be anybody, can decrypt the text. Well, what's the use of that? What's the point of signing something that anybody can decrypt because it's a public key? It may not even be secret. Well, the purpose is this. If Bob can decrypt this message using Alice's public key, then Bob knows that the message must have been encrypted with Alice's private key. And the private key is secret and confidential to Alice. So the only person, unless Alice lost her private key and somebody stole it, but other than that, the only person who could have sent this message is Alice. Okay? So it's digitally signing means encrypting something with your private key. which proves to people that only one person could have encrypted this message. Only one person could have sent this message. Nobody else could have created this message, okay? So signing is a form of non-repudiation. It allows everyone to know Alice sent this message. And by the way, Alice also cannot later deny that she sent the message. If she says, no, I didn't send you the message, then they'll say, wait, that's not possible. It was signed with your digital key. Only you know the private key, so you must have sent it. All right, so this is both a form of authentication and non-repudiation. Okay, and we also saw that in using RBNACL. RBNACL's simple box provides you a really easy way to generate private and public keys and to do signing and encrypting with the private key. So the way it works is that you have to ask RBNACL, please create a private key. Okay, and from that private key, this is Alice's private key, you can generate the public version of that key. All right. So now Alice has a private key and a public key. Bob can also have a private key and public key. And so now so for example, here's another kind of, so here's an example. So Alice is going to now send a message to Bob, and what she's going to do is she's going to create a simple box using Bob's public key and her own private key. She's using Bob's public key to encrypt the message to make sure that only Bob can read it. And she's using her private key to sign the message to show Bob that only she could have sent it. And on the other side, Bob, if he's expecting a message from Alice, will also set up a simple box with Alice's public key and his own private key. All right. And now what Alice can do is she can use her simple box to encrypt the message, and Bob can use his simple box to decrypt the message. So simple box gives you a very easy way, RBNACL gives you a very simple way to create public and private keys and do encryption and signing with it, okay? Any questions or recollections or doubts or thoughts about digital signing? Right. So that's the idea of what we're going to do this week. For certain routes where we cannot provide an auth token, we're going to ask the client application, the web application in this case, but it could also be a mobile application or some other type of application. We're going to ask it to sign its requests. So that prevents anybody from, that prevents any other application from making these requests. All right. So here's how it's going to look like. So with RBNACL, so the web application and the web API this time have to kind of work together. All right, and the application will be need to have a signing key, and the API will have what we call a verification key. All right, so the application will sign some of its requests, and the API will make sure that the correct application signed those requests. All right. So the steps look something like this. We need to create a signing and verification key. Now notice I'm not using the same simple box private key public key thing, because this public key private key that we saw previously was really meant for people to use their own private key and the other person's public key to send a message, and vice versa to receive a message. This time, we don't need to encrypt the message to the API. The web application does not need to encrypt the message to the API. It's already going over HTTPS. There's no point encrypting it twice. If you don't trust HTTPS, you probably shouldn't trust your own encryption system either. Because remember, HTTPS nowadays is using the same ciphers as NACL. It's using DJ Bernstein ciphers anyway, right? So we're going to use a different feature of RBNACL, which is called signing key. And signing key is just to sign a request, not to encrypt it necessarily. Okay. Well, it can encrypt it, but it'll encrypt it using a private key. So this is the way it works. We need to create a signing key, and the signing key is kind of like a private key. And from the signing key, we can extract a verification key, which is kind of like a public key. All right. And we will store these as, base64 encoded, because otherwise it's a long, ugly binary key. So we will just convert them into base64 integers. All right. And now when our client application, which means our web application, wants to make certain requests, for example, it's got, let's say, an auth token or something, some kind of JSON message, what we will do is we will create a signing object from the signing key. All right, so we will use the signing key to create this signing object, and we will then use that signer object to sign the message. Okay, and then when we send the message to the API, we will send the message in plain text, and we will send the signature attached to it. All right, as JSON, and then this can go out to the API. And the API, when it gets a signed message, it can extract the signature, and it can use the verification key. So remember, the signing key can give you a verification key. So the API will hold on to a copy of the verification key. And what the API will do is, once it'll create a verifier object. And once it gets a signature and a message, it will try to verify that this signature belongs to this message. Okay. It'll ensure that this message was encrypted using the signing key, the correct signing key. And what's really interesting, what's nice about it is, if it doesn't match, it doesn't. So if it matches, it says true. So you know that it's true. It was signed appropriately with the right signing key. That this message was signed by the person with the signing key that was used to generate this verification key. If it doesn't verify, then it doesn't just return false, it actually throws an exception, because this is considered an extremely dangerous situation. So RBNSEL actually throws us a bad signature error. So you've got to catch this error and deal with it then. All right. So this is how we're going to use digital signing to essentially ensure that certain routes which cannot have an auth token associated with it are actually coming from an authorized application. All right. Any thoughts or questions or doubts at this point? Like, what's going on? Why are we doing it this way? Any questions about this? You're all okay with this? Okay. Well, let me ask you like this. Could you use the raise hand button if you're okay with what we've done so far? Not if you have a question, but you really understand what we're doing so far and why we're doing it. All right. Okay, good, good. All right. Thank you so much. So, all right. So anyway, so this is the idea. We're going to be digitally signing certain requests to the API, which cannot have an auth token associated with it. Again, remember, if we have routes with auth tokens, I feel you don't need to digitally sign those requests. You have an auth token. You're trusted. You're good. Okay. This is only for routes for which we cannot have an auth token yet. All right. All right. So this is my implementation of it. You're welcome to have your own implementation, or you can kind of copy my ideas here. So what I've got, so on the API side, I'm doing a couple of things. First of all, the API now has a new library class called signed requests, a new file in the lib folder called signed request. And this is to help it verify requests that are coming in that are digitally signed. So this is on the API side. Now notice, the API is the one, in this case, the API is the one who's going to create the signing key and the verification key. Why? Because the API is the one we trust the most, okay? And we don't know where the requests are really coming in from, so it's the API who's going to create a signing key and a verification key. Similar to how certain companies provide you the signing key. They don't ask you, hey, please provide us a signing and verification key. They provide you the signing key. Okay, you don't provide it to them. So similarly, our API will generate a signing key. All right. Okay. All right. Okay. So this signed request class is actually also got a little class level method called generate key pair, which can generate a new signing key and a new verification key and return that combination. I don't use that in my application, but I've created a little rake task. In fact, let me jump to, where is my, is this the API? So this is the API. So in my API, I've got a little, where is it? I've got a rake task this week. So under the new key namespace, remember, I had like a new key DB feature and a new key message key task, and this time I've got a new key signing task. So this use the sign request library to generate the key pair, and it just prints it out to console. So I can say rake new key signing key, and for example, so this can generate for me a signing key and a verification key. Okay, and I go ahead and so the API only needs the verification key. Technically, the API only needs the verification key. It doesn't need the signing key. It can give the signing key to other people, to the web application. However, in my secrets.yaml, I keep a copy of both the signing key and the verification key on my API for the following reason. This time, when I write tests, right? When I create tests for my routes, which do not have an auth token, in my tests, I need to sign my requests as part of my tests. Like I have to simulate a client signing these requests. So for the purposes of testing, I also keep a copy of the signing key in my API as well. But I only use the signing key in my tests of my API. Okay. Okay. Riley, I don't understand your question. I was understanding after really code. Okay, you'll understand it more when you code the project. Okay. All right. Okay. So this is signed request, and it's so I use this generate key pair in my rake task. I don't use it anywhere else. Um, and and also for the purposes of testing, I've also got a sign method here which signs messages. Again, the API normally doesn't sign messages, it verifies messages, but I've created this method because it needs to simulate signing a request for testing purposes. Okay. But what the API's main code will really use is this verify method, which basically verifies a signature that it ensures that a message was signed correctly. Okay. And in the API's routes now, so for example, in the routes for registration, authentication, SSO, and so on, this time what it does is that for all these routes within the service objects of these routes, so within the service object of verify, registration, authenticate, authorize, SSO, let me see if I can show you one of these service objects. Where is it? App DB service object. So let's go to authenticate. All right. Oh, wait. Oh, no, hold on. Sorry. It's not there. It's here. So what I've done this week is that in my, where is my auth route? So basically, the routes, almost all the routes that need to be signed, all belong to this auth route. Okay, so it's like auth register, auth authenticate, auth SSO. These are the ones that really need to be. These are the ones that need to be digitally signed. So what I've done this week is, rather than verifying the signature in each of these routes, one really nice feature of Rhoda is within this auth route, before I get to these particular routes, I can just have a block that runs for all of them. Okay, so this block of code is run anytime routing comes through this auth route. Okay, before it gets to auth register or auth authenticate or whatever we have, it's going to run this block of code. And what this block of code does is it reads the JSON request, and it ensures that this is correctly signed. Okay, it makes sure that this is correctly signed. And if it's not signed, then I throw a 403 error and say this request must be signed. All right. So let me go back now to my signed request, and I'm using this parse method. And the parse method basically takes the signed JSON, all right, and it uses my verify function to make sure that the data and the signature match if I use the correct verification key. All right. So that's how I'm verifying all the requests coming into my API, not all my requests, all the sensitive requests coming in, particularly for authorization where I cannot have an auth token yet. All right. So this is the API side. I've got this new library, and then within my auth route, I'm just checking the signatures. So that means from the web application side, so let's go to the other application, our web application. This application now needs to sign all its requests, okay? And the way I do that is, for the web application, I have now got a new library called signed message. So this was my web API. Let's go to my web application. So my web application now has a library called signed message, all right? And all signed message does is, given a message, it uses the signing key and it signs the message, and base64 encodes it, and it returns a hash, which will be converted into JSON for transmission, with the original message and the signature. All right. And you'll notice that signed message. Okay, so that's signed message. Okay, and now all my service objects of my web application, which make the requests to the API, right? So what they do this time is, for each of my service objects that makes a request to the API, I've changed what is being sent. Instead of sending just the JSON version of the account or the JSON version of the credentials, I am now using signed message to sign this account. Or in this case, I'm using signed message to sign the credentials for authentication. All right. So two changes that had to be made on my web application: create this new library, which is really just this big, that's it. And then just change one line in each of my service objects that make these requests without an auth token. And all I really change is, instead of sending account.toJSON, I send signed message account, signed message credentials. All right, that's it. So now all the auth requests, at least, are signed by my web application with the signing key. Okay. And in my web application, let me go to, let me see if I set this up correctly. I've got a signing key now in my secret study YAML. Okay, great. So that's really all I want to say about this issue, about how do we ensure that certain sensitive requests that do not have an auth token associated with it are coming from a trustable source. If you have an auth token, then I trust you because clearly you have the user's trust as well to get that auth token. If a request is coming in without an auth token to a sensitive route, then I say, well, now I need to trust that you are the correct application, so please sign the request so I can make sure you are who you say you are. All right? Any thoughts about this? And the idea, of course, is that, I mean, in our case, we just have a simple web application. It's possible that you're working in a company where an API serves multiple web applications. In that case, each web application would probably, perhaps, have its own signing key, okay? You could use the same signing key, but it might be safer to have different applications use different signing keys. That way, if one signing key is compromised, you don't have to revoke all of them at the same time, right? Any thoughts, questions, concerns? All right. So that's part one of our three-part story about client-side security. Let's at least verify the clients for making sensitive, not yet authorized requests. All right. Okay, let's move on. The second thing I want to do today, and the third is going to be to talk about browser-side security. All right. Browsers are really strange creatures. We don't think of browsers as part of our system, but in fact, browsers are very much part of our web application, our system, because browsers are applications, just like a web application is an application. It just so happens that the browser already, your users already have a browser. You don't provide them a browser, but really browsers are simply part of your system. And that can be kind of dangerous because browsers can be used to conduct certain types of attacks on other users. So users can use the browser as a vehicle for attacks. So let me talk about a couple of types of attacks that are done using browsers. Okay, some of you may be very familiar with these, some of you may not be familiar with these. So I don't know how this is going to go. Okay. So the first type of attack I want to talk about is code injection, or more specifically, it's sometimes called cross-site scripting. Right? So in cross-site scripting, the idea is that somebody can use their browser to send some bad input to your application, and that bad input doesn't harm your application directly. What it happens though is if you convert that input into content that other people can see, then it could turn into a kind of payload, a virus or something that runs on other people's browsers. All right. So let me see if I can just show you a simple example. Maybe I should do it here. I'll show you an example later. I'll try to run a demo later. But let me try to describe it a little bit more first. And please do ask me questions. Before I move on, we do have a question about digital signing. So Yen, you ask, can digital signing replace the auth token of users? Nope. No, it cannot. And it cannot do that because the auth token contains a lot of information. It contains expiration dates, contains scopes, contains identities, and contains other things. So you cannot replace all of that with just digital signing. All right. So digital signing is a much more, I will say, conservative tool, just something that we use just to sign a message. It doesn't really, and actually, remember, when you're signing the message, you're using the signing key the API gave you. So it's not like the API cannot establish who you are, except it can establish that you have the signing key that I gave you. Okay, and you typically don't want to have a different signing key for every user. It probably would not make sense to do it that way. All right. All right. Okay, moving on. So let's talk about cross-site scripting. All right. So an example of cross-site scripting would be, let's say Eve or Eva comes to my web application, okay? And on my web application, I provide her some kind of form. It may be the login form, but it could be some other form like create a new project or do something else, okay? And what she could do is rather than typing in actual input, like, so let's say, for example, we're not dealing with my application. Let's say we're dealing with a like Facebook or Twitter or something like this, okay? So you go to Twitter and you need to enter your tweet, right? What you could do is rather than entering an actual tweet, you could just type in a script. Like you could type in some JavaScript and put a script tag around it, right? And this gets sent to my web application. And that gets sent to my API or whoever, and eventually a script ends up being stored in my database. No problem. My web application, my API is not going to run your script. It's JavaScript. It can only be run on the front end, at least in my case, okay? So it doesn't harm my application yet. You just entered a script, and that script is now stored in my database. So how does Eve hack my system? Well, she doesn't. What she does is she waits for another user to come, like Alice. And Alice comes to my web application and says, hey, let's say Twitter, and says, show me what's going on in Twitter. And one of the posts that shows up is Eve's posting, Eve's tweet. And Eve's tweet contains a script. That script gets sent back out of my database through the web application to Alice's browser. Now, Alice's browser, if it is not paying attention, will see this script and it might think it's just regular HTML and it'll try to execute that script, okay? And now Eve's JavaScript is running on Alice's browser. And imagine all the things you could do with that. You could use this script to just listen to what Alice is typing. Maybe she'll type in her username and passwords, all right? Or it could do worse. Maybe the script itself could redirect her browser to another page and force and maybe Alice doesn't realize she's been taken off of Twitter to some other site that looks like Twitter. A lot of things could happen. All right. So this is a classic example of cross-site scripting. For those of you who do web development, you may think, this is old stuff, Professor. Nobody falls for this anymore. No, cross-site scripting is huge to this day. This is an older story. This is from 2014, but this attack was actually conducted on Twitter, all right? Somebody actually posted this on Twitter, all right, this script on Twitter. And Twitter is pretty savvy, right? Twitter is a website that understands cross-site scripting, so they didn't execute it. Twitter will tell the browser, don't run this. This is not a script you should run. But this JavaScript was not targeting Twitter. The person who posted this, Andy, I suppose, was targeting people who were using a browser plugin for Twitter. That browser plugin is called TweetDeck. And I'm not exactly sure what it does. I think it helps people manage. It's like a dashboard for Twitter, basically. Okay, so it was a Chrome or Safari plugin that runs on the browser, and it's supposed to like enhance your Twitter experience. And what happened is TweetDeck, which is running on the browser, saw this. It interprets what's happening on Twitter and it modifies it. It adds a few features, makes a dashboard. TweetDeck was not expecting a script, and the plugin actually executed this script. All right, and fortunately, the person Andy who wrote this script as a demonstration to people of the vulnerabilities of XSS. And what the script really does is that if you look at the code, if you look at the JavaScript, this script is looking for the retweet button, is looking for the button that says share this tweet with other people. So when this appears on the person's Twitter, and if the person is running TweetDeck, TweetDeck will click the retweet button and send it out to all the followers of this person. And those people, if they're running TweetDeck, they will click retweet and they'll send it out to more people. This got sent. This got it's a virus basically. It's a browser virus, and this got retweeted and sent out to over 70,000 people before Twitter caught it and stopped it and like deleted this message. All right. So this is a great example of cross-site scripting. And again, Twitter may think, yeah, it's Stephen is saying this is a form of digital marketing. Wow, unfortunately, this is literally viral marketing. Okay, if you want to take the joke further. So, but this is a great warning. Your website needs to be savvy, but people are not just running your website; they're running on their browser. They've installed plugins and this and that. All of these things can be vulnerable. So your application could be vulnerable because somebody else is using a plugin that doesn't understand that this is not supposed to be a script, right? So this is an example of cross-site scripting. All right. And the classic way that I mentioned is that people literally enter a script, and if somebody else's browser opens it, they will run that script. Okay. And so a great place to run these things is on any place where people are sharing content. Anytime people are sharing things, this is a great browser side virus. All right. Alternatively, instead of running the script directly, maybe you're afraid that the browser will catch it. You may simply you may have a link that somehow links to a JavaScript or something that might in some other way get executed. All right. So links and scripts are both vectors through which cross-site scripting attacks are done. And what's really, crazy about this attack is Eve is able to run code on Alice's computer, right? That's crazy. So this is cross-site scripting attacks, and cross-site scripting attacks are still a huge problem to this day. All right. Let's talk about another type of attack. This is called cross-site resource forgery, and it can be used very powerfully, but so let me kind of describe what happens with cross-site resource forgery. And before I do that, let me just go back to cross-site scripting for a second. The vulnerability of cross-site scripting is that your browser trusts whatever is coming from the web application. Your browser trusts whatever is coming from the web application, and it just runs whatever is coming and says, oh, the web application gave me a script, let me run it. That's the breakdown in trust here. That's the vulnerable trust that people are exploiting here. They're exploiting the trust between the browser and the web application. Okay. Cross-site resource forgery is taking advantage of the trust between the user and the browser. Okay. So this is a different type of attack where we are taking advantage of the trust that the user has of their own browser. Why? Your browser is always trying to help you, okay? But sometimes it's a little too helpful. When your browser goes to any website, what does it do? It gives the cookies for that website back to the website, right? And the website can authenticate it and allow the browser to do whatever it wants to do. Now, somebody else can take advantage of this. So let's say here's Eve once again. God damn it, Eve, get a job. But here's Eve, let's say, okay? And what she can do is she can make a dangerous website, and for some reason you've come to this website, okay? And on the website, there's a link. And the link may sound pretty harmless, but what you don't realize as the user is that the link is not a link for Eve's web application. The link actually goes to a different website. And this website might be your bank, it might be Facebook, it might be Gmail, it might be some other website that you trust, okay? And what happens is when you click on this link, your browser is redirected to this website. And what does your browser do? Your browser faithfully passes the session cookie back to the website and authenticates itself. Now, whatever this link was trying to do, this other website trusts it. It says, oh, the user has come back with its cookies and it's making a request that's in the link. For example, let's say you have a dangerous route that for some reason you have it as a, let's say, as a GET request or even as a form, okay? This link could trigger that behavior. Let's say, for example, that this is Gmail, okay? And let's say there's a route on Gmail which, I don't know, changes your password, okay? What Eve can do is set up this link to go to that route to change your password, all right? Now, hopefully that route isn't so foolish that you can change the route with just a single request, but imagine with me that there's a dangerous route. And your browser faithfully passes back the cookies, so this service must do whatever this link is asking it to do, all right? Now, if it's a link, it's a GET request, so doesn't sound that harmful. What if it isn't a link? What if it's a post? What if you are filling in a form here and you're clicking the button, this button, but this button is actually is posting the request to some other website, not to Eve's website. Now, a post request can be pretty dangerous. You could make maybe like on Credence, for example, I may make a post request to add a collaborator to my project, right? So Eve's application has a link or a form, which I click on it, it sends me back to Credence, and it adds Eve as a collaborator on my project, right? And my browser sends the cookies, so my web application says, oh, you came with your cookies, I trust you now, right? You're logged in, you're asking to add a collaborator, I'll just do it. And my application doesn't realize that it's not Eve who's really, Eve is making the request. That's the problem. And not Eve, excuse me. The user is making the request, but the user doesn't understand that they're making the request. Eve's application has fooled the user to doing something that Eve does not have permission to do. Okay? This essentially makes your browser a confused deputy. And we talked about confused deputy problems before. Eve does not have permission to add herself as a collaborator to your projects on Credence. So Eve creates a link on her application, which if you, the user, logged into Credence, if you're already logged in, then you click on this link or click on a button and you submit a form to Credence, and then your browser does what Eve wants you to do. And since you're logged into Credence already, let's say, the link executes with all the privileges of this user. All right. So this is an example of cross-site resource forgery. Forgery means to make a fake, a fake version of something. Cross-site because Eve's application is now running requests on my website using the user's cookies that were on the user's browser already. All right. So obviously, my application now needs to be a little bit smarter. It needs to ask not only what is the browser asking me to do? It needs to ask which website is the browser just coming from? Was this link on my website or was this link on somebody else's website? So these are the kind of things that we now need to be able to do. Okay. There's other types of cross-site resource forgery, but I won't get into it. Okay. So I've got good news and bad news for you. The bad news, first, always, is the bad news is cross-site scripting is still a huge problem. The good news is cross-site resource forgery. It is still a problem, but is much less a problem nowadays because we have tools to deal with both these issues, but particularly cross-site resource forgery is a little bit easier to deal with. Okay. So I want to spend some time today talking about the solution to these problems. But before I do that, let's do a little demo. Let's do these attacks and see what it looks like, okay? But I'm not going to do the attack on somebody else's website. That would be fun. No, that would be dangerous. I will do it on my own. I'll make a website and I'll attack my own website. Okay. So let's go here. So I've made a simple web application, and I think I've got a link to this somewhere. It's right here. Okay, I may have modified it a little bit. So give me, before you clone it and run it, you may need to well, maybe you can clone it and run it today already. Okay, you'll need to bundle it. There's a whole bunch of gems that it uses. Okay. Um, and this is a web application. I'm not using Rhoda because Rhoda is a little bit more complex. I'm using a much simpler web framework called Sinatra. Sinatra basically allows you to just create routes just like that. It's super easy. Like you don't even have to like say make it. You don't even have to make a class. You don't even have to define like a routing structure. You can just start making routes like this. So this is all. This is my whole application right here. Okay, and I'm using cookies. My secret's obviously not so crazy, but I'm just using cookies. Okay, um, so let's see what this does. Oops, uh, excuse me. Okay, so let me run this from the command line. All right, and let me show you on my browser what's going on. All right, so this is running on localhost 4567. So let's go to localhost 4567. Okay, let's go to localhost 4567. What's going on? There we go. All right. This is a really, really silly application. As you saw, the code is only like 10 lines long. Okay. So what does it do? It allows me to enter some notes, and this application basically keeps a record of what I'm typing in. And I'm not using a database just to make the application simpler. Instead, I'm actually storing them in your own cookies. Okay. So let's try it. So let's say this is an application, and let's imagine that these notes that I'm typing in, let's imagine that I'm sharing them with my friends or I'm sharing them with public. In fact, let's imagine this is a simple version of Twitter. I didn't want to write that because I don't want to get sued, but let's pretend this is Twitter and I can write whatever I want, okay? So I am sharing my secrets here, okay? And let's imagine that my friends can read what I'm typing so that it's written here, okay? And some of these things are very, very private, okay? So these all kind of get recorded by this website. Now, time to attack this website. How do I attack it? Oh, look, I've got instructions that tell me how to attack this website. How convenient. I wish every website had this, okay? So let's do a little demonstration of cross-site scripting. I'll start with a very harmless attack first. So this says demo script. So I'm going to just paste it in there. Demo script, but within this input right here, I've got some JavaScript, okay? And when I hit enter on this, this will get stored on this website, and anybody who opens up this page or who's allowed to see this message, this will be sent to their browser to render on screen. And the browser is going to see, hey, there's some JavaScript in there. I'd better run it. So let's try it. What does it do? It opens up a alert box. It makes a little pop-up that says this site is vulnerable to XSS. Let's do it. Let's hit enter. Safari is a little too smart for me. Hold on. Oh, there we go. All right, sorry. This site is vulnerable to XSS. All right. This is not a message from my application. This is a JavaScript alert box that was created by my little script. Okay. So that was part of my demo script. Okay. Any other examples? Let's use this example. Thief script. This time, I'm writing a script that again opens up an alert box, but before it does that, it looks, so all of this is in a div element or something called board. So what this script does is it reads my screen, it reads what's written on my screen. And in this case, all it's going to do is it's going to show me what's written on my screen. But imagine this was some jQuery, and it's going to send it to another website. All right. So here's my thief script. All right. And when I hit enter on that, Safari does have a little built-in little thing. So thief script. Oh, in this case, it's okay. Vulnerable to SSS. Okay. So in this case, the script is unable to read it. I think Safari has some built-in security feature. Let me see if that works on Firefox. Browsers are getting a little bit smarter every day. Oops. Localhost. Oh, not 1992. Localhost 4567. Okay. So my secrets, and then let's put in the thief script. Okay. So apparently the thief script is not it's not able to. Oh, because it's running here. Okay, okay. It's running there. So let me type in some more secrets. Okay. This is only for my friends. Ta-da! Now the thief script, which runs second, is able to read everything that I'm typing. Okay. Everything that was entered after the thief script is now captured by this. All right. So this should also work on Safari. So if I some secret only for my friends. So the thief script should be able to steal this now. Okay. And this other problem. So these are all examples of cross-site scripting attacks. I'm able to run scripts on any browser that is showing this content. All right. The last example is oops, excuse me. In the last example, I entered a URL. I entered a link HTML, and that's provided as a link. If somebody clicks that, off they go. All right. So these are all kind of examples of, those were largely examples of cross-site scripting. The last is kind of an example of cross-site resource forgery. Okay, so where I'm providing you a link, you may say, oh, I'm safe. I'm on this personal notes website. Let me click the link, but the link's actually going to take you to another page where if you're logged into that page, you will do whatever this link is asking the browser, is asking that web application to do. Okay. So these are all examples of cross-site scripting attacks. What can we do to prevent it? That's why we're here today. All right. Here's some good news. The browser is the confused deputy in these problems. Okay, it's obviously the confused deputy, but it is possible to tell people's browsers how to handle these attacks and what to do. One thing many developers, unless you're very familiar with web development, don't realize is as a developer, you actually have a surprising amount of control over what the browser does while it's on your website at least. So we can actually now modify our web application to tell the browser of any incoming user to mitigate these attacks, to be aware of these attacks, and to prevent some of these attacks by setting up certain security policies. Now, we've seen policies before on the server side. Well, today, we're going to talk more about policies on the browser side. What is the web browser allowed to do and not allowed to do using your application? Okay, and it's more than just about when the browser is on your application. You can even tell the browser, if my application is embedded in somebody else's website, what can you do and what can you not do? So we can have a lot of control and power over the browser, and we just have to know how to unlock those features of the browser from our web application. Okay. So let's take a little break. We'll come back and we'll see how to fight cross-site scripting and how to fight cross-site resource forgery using policies and headers on the browser itself. All right, great. Let's take a little break. It's now 10:14. Let's take a nice long break. So about 10, 8:25, let's try to get back in business. So I'll give you a good 10 minutes. Go use the restroom, get some coffee, relax, whatever you have to do, and see you in 10 minutes. Okay? Great. And feel free to type in any questions into the chat box in the meantime.